Okay, these definitions are going to seem a little tedious, but they're necessary for things we're about to do. And when you break down the symbols, they're really not that bad. So, they're very similar in their wording, so I may only explain one and just say a few words about the second one. This says a function f has a absolute or global maximum at c if f of c is bigger than f of x for all x in the domain of f. So, think about what this is saying in symbols, okay? You have a function f, and this would be the function value, okay? This is the y value at c, okay? No big deal. The y value at x equals c. And this is saying that it's bigger than every other y value that there is, okay? So this y value is the biggest. So if that's the case, then we call it a absolute maximum, which makes sense. It's the biggest y value. Okay, we could also call it a global maximum. And then if you reverse that around, you get absolute minimum or global minimum. Okay, if we're talking about maxima and minima at the same time, we call those extreme values or extrema of our function f. Okay, so some Latin there for you as well. Now, this is talking about over the entire domain of f. So f, that could be all real numbers, or it could be a closed interval. Okay, -4 to 4, for example. If that's the domain of f, then we're talking about the biggest y value that occurs in that domain. Now, this is a similar definition for something else. So the wording is going to be very almost identical in most places. It says a function f has a local or relative maximum if f of c is bigger than f of x, so same thing. This is the y value at c, and it's bigger than all other y values, when x is near c. Now, that word near is kind of interesting, okay? Near means on both sides of. So if this is c, and we consider a neighborhood of c, which means both sides of c, we're talking about the y value here is bigger than all other y values around it, okay? It'll make sense when you start to look at pictures what we're talking about. So those values are called local extrema, or local maxes and local mins. All right, so here's a picture. Here's a function f, and its domain is -4 to 4. There are no other x values we're allowed to use. This is the entire picture. Okay, that's the assumption here. So the domain is -4 to 4, and this is our function f. So let's talk about some geography here. Okay. First of all, these are called endpoints of my interval. We talked about those in pre-calculus quite a bit. Those will never be local anythings, okay, because there's nothing to the right of this endpoint and there's nothing to the left of this endpoint. So when we talk about local, we're talking about on the interior of the domain. Okay, so we have this point right here at -2, -1. Okay, we would call that a local minimum because in a neighborhood of -2, -2 comma -1 has the smallest y value of all points in the neighborhood. Similarly, this point here at 0, 2, we would call a local maximum. In a neighborhood of x equals 0, that point has the highest y value of all other y values in the neighborhood. This point here at 2 comma -4 is also going to be a local minimum because in a neighborhood of x equals 2, that point there has the smallest y value. Now, those are local extrema. Now, if we consider the entire domain, then this point here, -4 comma 4, would be called the absolute maximum because this point has the highest y value of all y values in the domain. And then this point 2 comma -4 is not only a local minimum, but it's also the absolute minimum because it is the smallest y value in this graph. Okay, out of all possible y values, this is the smallest one right here. So part of calculus is figuring out where does a function have local extrema or absolute extrema, and we're going to find some techniques that teach us where to look. Before we get there, let's talk about a theorem. We're not going to prove this theorem. It probably seems obvious, maybe not. It's called the extreme value theorem. So we had the intermediate value theorem, which was the in-between value theorem. This is now the extreme value theorem. So we're talking about extreme values of a function. It says if f is continuous, we know what that means, and is located on a closed interval a to b. So we have a restricted domain, that has endpoints. Okay? If those two things are true, then f will always have an absolute maximum and an absolute minimum somewhere on the interval AB. So this theorem guarantees you that a function has absolute maxes and mins. It doesn't tell you where to look. That's what we're about to discover, but it tells you that they exist. Okay? Now, there are two pictures here that are going to show us why these two conditions have to be met for the theorem to be true. Okay, what two conditions? F being continuous and F being defined on a closed interval. Okay, I don't know if you can see it, but this first graph here has an open circle here at x equals 0. So this function is not continuous. Okay, not continuous. So this theorem is thrown out the window, does not apply. So this function does not have to have an absolute max and an absolute min. Now it has absolute minima, has two of them. These two y values down here would be absolute minima, but this function does not have an absolute max. It would be where this open circle is. But since there's no dot there, we don't actually get to that y value, and there is no y value right before that y value. Okay, that's part of the properties of real numbers. There is no number next to a number. There's always more numbers in between. So this function has no absolute max. It does have two absolute minima, though. Now, this function, I don't know if you can see, has open circles at both of its endpoints. So this function is not continuous, and it's also not defined on a closed interval, AB. It's defined on an open interval, AB. And for the same reasons, this function does not have an absolute max, because it would be where this open circle is. But there's no dot there, and we can't say that there's a number right before where that dot would be. And same thing down here, there is no absolute min because there would be if there was a dot there, but there's not. So this function has no absolute max or min. So those criteria have to be met in order for there to be guaranteed absolute maxes and mins. Okay, so where do we look to find absolute maxima and minima? Okay, first of all, we have to agree it's impossible to test all x values in the domain of f. You can't do it because there's an infinite number of them. We don't have that much time, and we couldn't do it even if we had as much time as we wanted. So we can't do it that way. We probably don't want to guess, so there's going to be some tests that we do to figure this out. Okay, we're going to explore two functions on our calculator that will help us determine where do we look to find Extrema. We're going to go ahead and explore a couple functions here. The first one's going to be x to the fifth minus 4/3 x cubed plus 6. And I can't quite see what happens in this region, so I'm going to change the window a little bit just so I can see what happens up there. So maybe change the y max to 15, and that's pretty good. Okay, there's going to be a couple points that we are going to look at here. We're going to look at x equals -2, where there appears to be a local maximum. We're going to look at x equals 0, and we're going to look at when x is 2. Now, there's a command here in the menu that I want you to get acquainted with. Okay, so under menu, if we go to Analyze Graph, and we choose dy dx, okay, that's the symbol we know means derivative. And what this will do in this screen, it will find the slope of this curve if I give it an x value. So, dy dx, I click Enter. It asks me for a position. And if I enter in a left parenthesis, so for me that's Shift 9, then this little screen here pops up and I can enter in an x value. So I'm going to enter in a -2. It will automatically calculate the y value if I press Enter. And there it puts a dot where I wanted to look, and it tells me that that dot, the slope of the curve is 0. We'll take a look at that in a second. All right, let's repeat the process for x equals 0. Okay, when x is 0, the slope is also 0. And let's do one more. When x is 2. Okay, places a dot there for me. The slope there is also 0. Okay, now real quick, let's just do this for one. We'll do a zoom box, and let's zoom in on this point right here. And I'm continue to use zoom box to zoom in on this dot. What I want you to see here is that the more I zoom, not only does my graph become linear, but my graph becomes flat. Okay, becomes flat. So places where the slope of the curve is 0 will be locally flat. We've talked about that before. And let me go back to Windows Zoom and use the standard window. So there were 3 spots on this graph where the slope was 0. One was a local maximum, one was a local minimum, and then this point right here, let's do some zoom box and see what that's all about. Okay, it gets flat, but if you saw what I just did there, this is not a maximum or minimum, okay, because we go from having y values that are larger to y values that are smaller. So even though the slope was 0 there, the graph is flat, this is not a local max or local min. Okay, now let's take a look at another function. This one's going to be the absolute value of 4 minus x squared. And let's use that same command where I think I see local maxes and local mins. So we want analyze graph dy dx. So I think there's a local max at 0. Okay, and once again tells me the slope there is 0. And let's take a look at these other places here. This looks like -2. There's a min. So let's enter in -2. And it tells me, interestingly here, the slope there is undefined. Okay, this is one of those jagged edge cusp things. Corners or kinks, whatever word we want to use here. And let's just double check this last point here, which looks like it's at x equals 2. Okay, also a slope that's undefined. Okay, so I pasted the 2 pictures that we used, and let's take a look at the data that we recovered and see if we can make a conjecture here about where do we look for maxes and mins. All right, on this first graph, there were 3 places where the slope was 0. 2 of those were either a local max or local min, 1 was not. So it's not automatic that if the slope is 0, you have a max or min. Okay, but that is a good tell that that's possibly a local max or min. Now, is it necessarily true that if the slope is 0, if there's a max or min, then the slope is 0? The second graph proves that that was not the case because at these 2 spots, the slope was undefined, but you had local mins. So we have kind of an idea now of where do we look. Let's define a concept here. If f prime of c is 0 or f prime of c is undefined, then those are called critical numbers of your function f, okay, because chances are some critical things are going to happen there. So we have a word that means critical number. And this will lead us into how do you find absolute extrema on a closed interval? All right, number 1, you find all the critical numbers of f and then plug those numbers back into f. So what are the critical numbers? Places where the first derivative is 0 or undefined. So we find those y values, and then we find the value of the function at the 2 endpoints. Okay, we do that because if we go back to this picture, this function had a maximum at an endpoint. So that also needs to be checked. And a lot of students forget to do that. Okay, and then we just compare. The largest of those values is the absolute max, and the smallest is the absolute min. So this method creates a way to find a list of numbers to test, and those are the only ones we need to test. There's no other place that maxima and minima can occur. They have to occur at either places where the derivative is 0, or where the derivative is undefined, or at an endpoint. Okay, so here's an example. Find the absolute max and absolute min of g on the closed interval 0 to 6. So we have a closed interval, and we have function g, which is a polynomial which is continuous. So we know these values must occur. So who are my candidates? Well, automatically we have 2 candidates. They are the 2 endpoints of the interval. So we have to test g of 0 and g of 6. We know that going in. G of 0 is going to be 2, and g of 6 is going to be 14. Okay, and you can check my work if you want. Now, the only other places to look are critical points, or critical values. Those are places where g primed is 0 or g primed is undefined. So let's find g prime of x, and we'll work from there. So g prime of x will be 3x squared minus 14x plus 8. That's never going to be undefined. It's a polynomial. So we'll look and see where this is equal to 0. And hopefully we can factor this fairly easily. Otherwise we'll go with the quadratic formula. So we know we need a 3x and an x. And I think if we go minus 4 minus 2, we'll be good. Negative 12 minus 2 is negative 14. Good. So this means that 3x minus 2 is 0, which means x equals 2/3 is a critical number. And x equals 4 is a critical number. So those are the other 2 places we need to check, and that's it. That is our exhaustive list, which is a lot better than trying to test every possible point, which is impossible. Okay, so g of 2/3, for the sake of time, is a nasty decimal, but it's about 4.518, and g of 4 is going to be negative 14. So I go to my list, and I look for the biggest y value. Okay, this is the biggest y value on my list, so this is the absolute maximum. And I look for the smallest y value, which is negative 14, and that has to be the absolute minimum. I'll pull up a picture of the function so you can take a look and see if you agree. But that's a nice method for finding maxes and mins without having to go searching through a lot of points or even having to graph the function. This picture of the graph, you can see the domain is 0, and this is actually 6 way out here. If we thought the absolute max occurred at x equals 6 with a value of 14, so there's the value of 14, and the minimum occurred when g was 4. Okay, if this is 6, then it's reasonable that this is 4. And we saw that the critical points were 4, so there's a slope of 0 at a local min. And x equals 2/3 was not an absolute max, but ended up being a local max.